In the last episode, we see how mission a journey to Mars landing, collecting samples, and returning them to Earth to prepare for humanity's first footsteps on the red planet. Year 2035. This is the first modular lunar base segment to be delivered to the Moon in year 2035. Humanity extends beyond Earth to construct a foothold on the lunar surface. The objective: deploy a self-contained habitat module powered entirely by solar arrays, demonstrating reliable power and life support systems without permanent crew on board. Which trajectory will the supply vessels follow? And how will the module orient its solar wings to endure the fortnight-long lunar nights? How will Mission Control manage these delicate systems from almost 249,000 miles away? Over the months that follow, how will thermal loops adapt to temperature swings? And what happens to the batteries and electronics during extended darkness? Why is this base placed near Shackleton Crater's rim? Because its elevated terrain offers near-continuous sunlight for power and potential access to water ice in nearby shadowed hollows. The journey begins now. The spacecraft departs Earth atop a heavy-lift rocket. The fairing encloses the habitat module, its folded solar wings, and a telescoping communications mast. After ascending under 3 times Earth's gravity, the upper stage reignites, sending Luna-Solar 1 toward lunar orbit. In Mission Control's Operations Center, engineers monitor telemetry as the vehicle departs Earth's gravity well. Days later, the lander detaches from its transfer stage, firing engines to decelerate from orbital velocity into a controlled descent. Landing legs extend and flex, accommodating uneven regolith, and the module settles gently onto the rim. Fine dust billows in a gravity well 10 times weaker than Earth's, settling after a few dozen seconds. The first modular base segment has arrived. Shortly after touchdown, the lander's robotic arms unfold and lower the habitat onto the crater's slope. Adjustable struts level the base on irregular ground. Next, the communications mast descends, its ground anchors driven into the regolith to resist micrometeorite pings and occasional moonquakes. From Earth, Mission Control issues the power-on command. Radioisotope heaters activate, preserving delicate electronics above -4 degrees Fahrenheit. Battery packs engage, verifying voltage health. Then the solar wings begin their automated deployment. The solar arrays swing outward in sequential stages. As sunlight spills across the rim, stepper motors pivot the panels to capture maximum energy. Within minutes, kilowatts of current flow through a central power management unit, which conditions and distributes high-voltage power to life support simulations, environmental sensors, and communication relays. For nearly 2 Earth weeks, the module enjoys uninterrupted solar illumination. Engineers observe stable voltage levels, while panel temperatures hover around 104 degrees Fahrenheit in direct sunlight. Radiator fins on the base's exterior shed excess heat into the black sky. As daylight wanes, ground teams prepare for eclipse. Known essential systems shut down, and batteries assume the load to power heaters that protect fluid loops and electronics. Internal thermostats maintain a moderate core temperature despite external plunges to -274 degrees Fahrenheit. Multi-layer insulation blankets wrap the habitat, slowing radiative heat loss. During the 2-week night, the module enters low power mode. Solar arrays fold slightly to reduce dust accumulation, and communication switches to a heartbeat beacon at reduced data rates. Mission Control tracks heartbeat signals, indicating battery charge, internal temperature, and coolant pressure all remain within acceptable bounds. When sunlight returns, power pours back through the arrays, recharging batteries and reactivating full systems. In the ensuing weeks, the module activates its science payloads. A trio of accelerometers begins logging tiny micrometeorite impacts. Seismic sensors record tremors triggered by tidal stresses. A regolith sampling drill penetrates about 6.5 feet beneath the surface, delivering lunar dust to onboard spectrometry. Results reveal that nearly half the regolith's mass consists of oxygen-bearing minerals, with detectable traces of hydrogen bound in hydroxyls. These data validate future plans to extract breathable oxygen and water from lunar soil. Meanwhile, small rovers tucked on the lander deck roll out to map the surrounding terrain, capturing panoramic imagery to create a three-dimensional model of this polar plateau. Several weeks after landing, the regolith processor initiates its inaugural water extraction experiment. The sintered oven subsystem collects 220 pounds of lunar soil. Heaters gradually raise the temperature until water vapor sublimates. Condensation chambers yield roughly 2.2 pounds of purified water, confirmed by the onboard spectrometer. Concurrently, an oxygen reduction trial begins, electrochemically converting processed regolith into oxygen gas, which is routed into a small test thruster. A brief impulse maneuver demonstrates that a propellant feedstock derived from lunar soil can produce measurable thrust, paving the way for fuel harvesting in future missions. Thermal control remains critical. The habitat's heat exchange loops circulate a sodium-potassium eutectic fluid, which must remain above its melting threshold. Hours before each nightfall, electric heaters revive fluid temperatures. Engineers refine algorithms to balance heater power and battery draw, preventing coolant freeze without draining energy reserves. Across multiple night cycles, autonomous routines correct minor thermal deviations and perform a responsive reboot whenever transient faults occur, underscoring the importance of radiation-hardened hardware and robust software safeguards. Months into operation, the lander's robotic arm completes over 200 autonomous tasks, adjusting solar panel angles to optimize power, repositioning radiators to handle thermal loads, and clearing obstructive rocks around the module's perimeter. Equipped with stereo cameras and light detection and ranging, the arm maps terrain and identifies obstacles within a 10-foot radius. Exterior inspections reveal micrometeorite pitting on protective panels, measuring under a millimeter well within design tolerances. Inside, life support analogs operate at minimal loads. A compact gas chromatograph analyzes vacuum samples drawn from the exterior to characterize trapped volatiles, and nitrogen inflators verify the integrity of pressure seals. Humidity sensors monitor trace water vapor outgassing from interior components, ensuring environmental stability. Telemetry reports the delivered mass of the module at about 20,000 pounds, including about 4,400 pounds of battery packs, 2,200 pounds of structural struts, a regolith processing suite, and about 1,100 pounds of scientific instruments. Descent maneuvers consumed a delta-V budget of about 1.7 miles per second, executed by dual hydrogen-oxygen engine burns totaling several minutes. Hydrazine thrusters handled fine attitude control. Landing legs absorbed irregularities, extending up to about 10 feet to compensate for sloping terrain. Precision navigation algorithms, backed by Earth-based tracking, placed the module within a 660-foot ellipse, guaranteeing continuous line of sight to ground stations. Long-term solar array degradation is closely monitored. After several lunar days, output dips by about 2%, attributed to ultraviolet radiation and charged particle bombardment. Engineers adjust tilt schedules, aiming to reduce peak radiation exposure. These arrays are rated for 15 years, so early performance metrics will inform design choices for future large-scale installations. The regolith processor, having repeatedly heated samples up to extraction temperatures, consistently draws more power than initial estimates. These observations prompt design reviews of thermal insulation and heater efficiency for the next-generation processing unit. Communications rely on a high-gain antenna atop the mast, downlinking several megabits per second of science data and receiving command sequences at lower rates. A low-gain patch antenna maintains a simple beacon when power is restricted. The link budget factors in free space loss over almost 249,000 miles and atmospheric absorption around Earth's ground stations. With a 1.3-second delay each way, onboard autonomy manages immediate fault responses. Engineers deploy advanced artificial intelligence routines that detect anomalies within milliseconds, transitioning systems to safe mode when any sensor reads out of bounds. Dust mitigation experiments commence when fine lunar particles adhere to the solar cells. Within just a few days of exposure, efficiency drops by 0.5%. Ultrasonic vibration cleaning cycles activate twice per lunar day, shaking away adhered dust and restoring nearly 95% of peak performance. These findings prove vital for planning large solar farms, where dust accumulation could drastically reduce power output without regular cleaning. After more than 2 lunar cycles, the module achieves a milestone: 60 days of continuous operation. Batteries have cycled through repeated charge and discharge cycles, powering heaters during extended nights. Micro-vibration sensors detect minor moonquakes, offering new data on local seismic activity. External temperatures swing from scorching highs when sunlight strikes the rim to freezing lows under a starless sky. Internally, the habitat core remains within design specifications, fluctuating between just below freezing and a few degrees above as autonomous thermostats respond in real time. To prepare for crewed visits, engineers introduce a virtual crew operations experiment. Software mimics astronaut tasks, instructing robots to fetch tools, swap a malfunctioning heater resistor, and test the pressurized hatch. A small quadruped robot, nicknamed Lunabot, hauls components to the robotic arm, which then performs precise maintenance moves. Video feeds confirm each step, verifying telepresence control from Earth. Radiation dosimeters inside the habitat measure background exposure, confirming that layered shielding reduces internal doses to acceptable levels for short-duration stays. As the module continues to operate, Mission Control compiles key performance metrics. The habitat endured multiple day-night cycles without human attendance. Solar arrays functioned at near-peak capacity for most of the illuminated period. Regolith processing delivered demonstrable quantities of water and oxygen. Communications links achieved greater than 99% availability. Dust cleaning procedures proved effective in preserving power output. Thermal systems kept interior temperatures stable, despite external swings exceeding hundreds of degrees. Robotics performed hundreds of autonomous tasks with near-perfect success. Each data point informs the design of subsequent base segments. For now, the base stands silent but alive. Shackleton's rim casts dramatic shadows as sunlight arcs across the horizon. The habitat's antenna remains vigilant, ready to receive new commands. During solar events, radiation shutters close, and systems enter protective standby until conditions stabilize. Micrometeorite impact sensors log each microcollision, transmitting data back to Earth. This lunar outpost has not yet hosted humans, but it thrives as a living laboratory, proving that long-duration operation is feasible on the Moon. Looking forward, this module will be joined by additional segments power units, research greenhouses, and habitation rings forming a network base capable of hosting rotating crews. The successes and lessons of year 2035 will guide lunar infrastructure through the year 2040s, enabling resource harvesting and deeper exploration. For now, the silent module stands as proof that human ingenuity can transform a barren landscape into a thriving outpost of science and discovery. In the next episode, we will see how humans and robots land on Mars in year 2038 for a historic 30-day mission and return safely to Earth.